Welcome, everyone. Sarah, do you go to your OTH classes? Oh my God, okay. Well, it was really fun because the OTH person, it was their first day, and one person was on time. Because Matt has he's got a new job. He is working on a landmine detector. I know, pretty cool. So he's working for a charity that is building like a landmine detector, which is pretty dope, I gotta say. It's pretty, hello, come back. Physics time?
Sorry, how much do we have left?
No, go on. Let me show you a trick. Come here, watch this trick, Okay, you ready? Watch this magnet. Okay, everyone, we're gonna watch this trick. Watch this magnet. Ready? Watch this. Did you see it hit the ground? Okay, now watch. I'm gonna put it inside the tube. Are you ready? Yes. What in the world is going on? Look at this magic trick. In the tube it goes. Still going. Well, maybe it's coming out the other end. Hang on. I'm doing a little pantomime here, right? What's going on? That's what we're learning today. Why the heck is that happening? Look at that. Come on. There we go. If anyone would like to play with the tube during the break, you're more than welcome to. I got it. It's okay. I will attest this tube is non-magnetic. You can go to your class now, sorry. I just want, you're an adult, you can do whatever you want with your life. Physics.
Oh, okay.
What degree are you doing?
I'm studying computer science.
You have to do Physics 1A at some point, right?
Yeah.
Are you doing it now, this term? All right, well, you'll see me when you do it next term then. Yeah, bye-bye, bestie, good luck. See ya. All right, so this is non-magnetic, right? It's just metal. And via magnetic spook, behold, it's just not coming out. Right? What's going on? Well, let's find out, right? There it is. Good. So yes, that is somewhat related to Lenz's law. Well, Lenz's law is a condition on that. So today, we're learning about Faraday's law of induction, where induction is the process of inducing, a current inside a metal object. It's how we generate electricity. And we're going to talk about Faraday's law in terms of equations we already know. Okay? So we are technically learning a new equation, but it's just that two things we knew are equal to each other. That's Faraday's law. It's not too bad. Okay? And then we're going to solve allegedly complicated questions. They're not that bad, honestly. So the relevant prior knowledge is magnetic flux from last time. Now, if you remember, magnetic flux is just electric flux, except you swap out every instance of electric for magnetic. That's all. Did you have a question, or is just that's your hand resting spot? Just making sure, right? No, you keep your hand resting there, it's fine. I just wanted to double check if you like asking a question. Is it too hot in here? You ran here? Something like that, yeah. Room control, air conditioning, it's on. Slay bestie, that's all I can do. All right, who's ready for the next test next week? Well, don't forget we've got our revision session Tuesday at 6 p.m. Yeah, Tarek. Yeah, it'll be on Discord, and I recorded it. The problem is, hang on, let me turn off the microphone. Okay. The problem is because I go over questions that are in the exam, I can't publicly post it. So it's on Discord, and I like the links, the YouTube videos are on Discord too, and I'm sure if you ask someone to just send you the YouTube link, but what people do is they just paste me questions. I say, give me whatever question you have. And it always ends up being questions that are going to be in the exam. Right? And hope I didn't talk about that. Oh, that's okay. I can edit the lecture recordings. So that is why it's on Discord, and that is why I post the recording as a private link. It's not a public link, because like we all know what's up, right? But I don't want to get fired. So, right. And that's why that is. Anyway, so we had to learn magnetic flux. We learned it last week. And then I hope you remember Ohm's law. Ohm's law is that the voltage across a component, or the voltage drop technically, is equal to the current through that component multiplied by the resistance of that component. This is what we learned. We learned this in high school, I hope. Americans, did you learn that in high school? No. Great. Okay. So to begin, who would like to be a wizard? Who wants to be a wizard? Need a wizard? All right, Sarah, you're up. Come be a wizard. I am in the middle of reading Lord of the Rings, so you know. Behold, all right, Sarah. So Sarah, my assistant, will prove to you that this is no sleight of hand. Sarah, hold the tube and insert the magnet into the tube. Drop it in. All right. Behold. Behold the wonder. Where is it? There it is. It took so long to fall out. Now, Sarah, drop it next to the tube, adjacent to it. Observe. Gravity. So what's happening there, right? What is going on? Why? You know, I'll hand it to you, and then you can hand it back to me, and we'll see, is it in there? You know, we can do a whole pantomime, right? Like, you can look through it. You can see it in there. Maybe don't, be careful. Don't look so that it comes out. Look in there. Can you see it? Yeah, it's sliding down very, very slowly, right? It's not because the magnet is large relative to the tube, because the magnet is much, much thinner than the inside. What would you say the ratio of these sizes are? Yeah, a lot, right? So this magnet, thank you so much for your assistance, Sarah. Everyone, applause. Woo, right? It's not that the magnet is like sliding against the surface, right? There's some property of magnet and some property of metal that allows this strange behavior to occur. So it's the same thing that happens in most of the interesting electromagnetic phenomena we get. And here the key term is electromagnetic, because we are dealing with the intersection between the electric and the magnetic. And it is essentially this thing called Faraday's law. And Faraday's law tells us that in circumstances where there is a changing magnetic flux through a conductor, and any metal is a conductor, right? The changing flux will attempt to, not necessarily successfully, but attempt to induce a current in that conductor. Now you might be thinking, well, Tom, how the heck does that actually make the magnet slow down? I'll get there, don't worry. All right? But the first thing we must understand is this, that an induced voltage, which we will call EMF, which we will very unfortunately also use epsilon for, in addition to electric permittivity. I'm sorry. But the EMF generated by a changing flux is the derivative, the time derivative of flux. So if you take an object and you derivative the flux through the object, you will figure out how much voltage is induced along that object, right? Now there is a direction component to this. We will come back to it later, right? There is, as you can imagine, in second and third year, complicated bullcrap mathematics. For us, nah. It's just that you take the derivative of flux with respect to time, and that is equal to this thing called EMF, which I want you to think of as voltage. What this means is if you take any loop of wire and you induce a change in flux, be it via turning up or turning down a magnetic field, be it via moving a magnet, right? If you induce any sort of change in magnetic condition, the material will experience a voltage, and if it experiences a voltage and it is able to make a current, it will experience a current. Tarek?
So does this kind of depend on a particular structural relationship between components,
The structural component that we have here that matters is the fact that we're using flux, not magnetic field. Because remember, flux is the integral over an area of it's the cumulative magnetic field. So you're entirely correct. If I had this big loop versus this small cross-section, and I had the same magnet, we would get a more pronounced effect with the big loop than we would with the small loop by virtue of the area being bigger, right? So there is a physicality to it, and that's why generators that we use to generate electricity are freaking gigantic. Right? Because bigger coil, more flux, bigger derivative, right? If you imagine you have, like let's say you have, for example, flux, let's say you have a pen, right? If you had most common, it wouldn't be a me lesson if this didn't happen, would it? Hey. Right? If you had flux was equal to like A cos omega t or something, right? Which is what we commonly get. We commonly get a sinusoidally varying flux. Then the derivative of that is A sine, right? And that A, which is the maximum flux, changes completely how much EMF you get. And that's why we have a gigantic coil in generators, because you want huge amounts of flux. Right? So that's very, very astute. And that's why flux instead of magnetic field is important. And that's also why magnetic field is sometimes referred to as flux density, because it's really the flux that, like, it's the flux you should give a flux about, right? When we're talking about actual induction, actual interesting stuff. Now, epsilon is electromotive force, EMF, it's volts, it's voltage, right? It's just like a regular voltage, only crunchy? No. That was a serial reference. People from not Sydney, it's a stupid serial we have, they had an ad. And phi b is magnetic flux in Weber, WB, or Tesla meters squared. Okay? And we'll learn how to figure out the direction a little later. But the first thing is, if you take the derivative of flux, you get the induced EMF. So let's give it a try. We've got a circular loop, radius 0.5 meters. It has a magnetic field of this function. What's the EMF along the loop? Well, step one, we need to work out phi. Step two, we need to differentiate it. So, of course, we're assuming that phi equals B times A because my B field has no spatial dependence. My B field is constant in space. It is no longer constant in time. It varies with time, but that doesn't matter for us because the integral that flux cares about is a spatial integral. It's integral dx dy, or integral with area. So the magnetic field is constant in a given area at a certain time, is the idea. That's why we can use B times A instead of integral B dA. And unfortunately, we are getting into things that vary both in time and in space, which we'll do next week with waves, right? I won't do it, you'll do it, right? So, that's equal to what? Okay. That's equal to 1.45 t squared minus 1.2 t, all multiplied by the area of this loop. And the area of this loop is just going to be, well, that's r, so it's going to be 2 pi times 0.5 squared. Wait, regular pi? I don't even know how to do the area of a frickin' circle, right? And then so that's going to be equal to, I'm literally just going to write pi 0.5 squared outside of 1.45 t squared minus 1.2 t, because I'm literally that lazy. And then the EMF is equal to minus d this dt. Right? I'm not writing phi subscript b, I'm just writing phi because we're not dealing with electric flux. You will never deal with both of them at the same time in this year. So you don't have to worry about it. And so that means this is going to be equal to the derivative of that. So that's pi times 0.5 squared at the front. Finally, we get to do a derivative, right, instead of an integral. Isn't this so relaxing? Isn't this chill, right? Times 2 times 1.45 t minus 1.2. Right? I really hope I didn't flub, literally the easiest derivative of all time. But that would be the electromotive force, right? It still depends on time, right? In reality, you are very unlikely to get a B field that is unbounded in time like this, right? That theoretically increases to infinity. That's cursed. In reality, of course, it's a sinusoid, right? Most B fields are periodic functions, right? And there's a reason for this that you'll get to next week when you talk about electromagnetic waves, which are these kind of self-reinforcing periodic variation in electric and magnetic fields. But that's next week. For now, you take the derivative of it. That's EMF. Slaying. Question?
We need the negative sign in front of it.
Oh, hell yeah! What kind of dumbass forgot this negative sign? Good. Thank you. Now, this is good. I would say that it's a test, but it's not. I'm literally this stupid. So I run a tutorial as well for 1A. And in my tutorial, I did a demonstration integral. And I screwed up two things. One, it was x plus a to the 3/2 on the bottom. No, x plus a squared on the bottom, even easier. And then it became x minus a for some reason when I was transcribing it to another line. And then it also went to the numerator for some reason. And I was so confused because the answer came out really weird. And they're like, sir, to the -1 means it's on the bottom. And I'm like, oh yeah. And then someone came up to me and said, you've made me feel so much better about feeling like I'm not smart enough to be a physicist. Which is true. I'm a physicist, and look at all the dumb mistakes I make all the time, right? So the next thing to be aware of, if you are doing multi-loop systems, so let's say, for example, you have the same flux, but it's through 5 loops. So you took a loop and you've layered it on itself 5 times, you multiply it by 5. That's it. You just multiply it by the number of loops. That's all. So if you have multiple loops, it's just like how, if you remember, when you have multiple loops of a solenoid, because as you will do next week in your lab, I just realized, when you have a solenoid, the more turns there are of the solenoid, the more magnetic field there is. Similarly, the more turns there are of this solenoid, the more EMF you get, because each loop gets d phi dt EMF, and so if there's more of them and they're all connected together, that voltage all adds up. That's the idea. It's like connecting several batteries in series. That's the idea. And so when you look at your formula sheet, you'll actually see it as EMF equals minus n d phi dt, because technically n is the number of loops, right? Now, it could be a circle, it could be a square. Notice how the geometry of the loop is baked into phi, because phi is b times the area, right? So theoretically, this equation is geometry agnostic, but that's only because it assumes you've figured out phi already. And phi depends on the geometry if you only know b, right? So this is a problem. You have to do a geometric problem to find phi, and then it becomes a temporal problem, time-based problem, because it varies in time, right? I hope you're getting a glimpse at how things can get weird in physics. I was trying to avoid saying a swear word. Yes?
Where's that voltage measured? Where's the difference in EMF?
Correct. And this is why we don't technically call it a voltage, because it is measured in volts, but it is not between 2 points. I will show you a little later. It is defined as a path integral, right? The EMF is defined as the integral of the electric field over the path. So it's got the same units and the same definition as a potential, right? But the reason we don't call it a voltage is because it's technically a cumulative change in electric field. A cumulative electric field over a loop, right? But that is exactly why it's not called voltage. It's technically called EMF, right? Astute question. And that's actually my last slide, is to go through. So that's good. I'm always gratified when people ask questions that I also asked myself when I was writing these slides and gone, hang on a second. But yes, so there is a reason, and we will come to it when we look at the Maxwell-Faraday law or Maxwell-Faraday relationship or something. It's there. It's there. I promise you the answers are coming. But for now, we pretend that we can just pretend it's a voltage. All right, for now. Okay, even though, yes, voltage between which 2 points, Tom? None, right? It's just the magic voltage, which runs counter to everything I've ever told you about voltage, which is why it's called EMF instead, right? And if you are given the resistance of the doodad, the circuit, they'll just say resistance equals blah, then You take whatever the EMF you have developed and you divide it by the resistance, and that becomes the current. Does anyone know where I've left my lecture notes? What? I had some in my hand. Oh no. Oh no. Oh, am I going to have to remember exactly how many slides I wrote? This is the problem because I forget how many slides I have. Oh, God, they're printed off somewhere. All right, well, we'll find them during the break. I've got a watch. That's all. That's 1 second. This is so me. This is what I gift you in our last lecture. Complete chicanery. Well, I printed it out somewhere. Anyway, whatever. I just use it to keep track of where I am. Luckily, there were no derivations today I need to know. You have a question? Yeah.
So if EMF is in between 2 points, is then resistance not between 2 points?
Resistance is, yes.
Is it like the...
So technically it's the integral of resistivity over the path. Correct. But you won't get a question like that. You will only get a question just telling you the entire loop resistance. And you'll have to assume that it is a constant resistivity around the entire path.
Okay.
It's stupid. Yes. It's, because you're right, what we should be expressing it is we should be expressing it as I, at any point, is equal to the infinitesimal, we could give it infinitesimal voltage, and we could divide it over some infinitesimal resistance, right? Yeah. And that's how we should do it. You're not wrong. I will say, I look at all the assessment questions to this module, and I write things according to those styles, is how I'll say it. But that is the completely correct way to think about it. And I don't know, that's just unfortunately how things are. What? Oh, okay, good. Someone talking about International Women's Day. Slay. All right, so let's try this next one. Hang on, I'm going to put freeze frame up. This is, I'm busting out the techniques I have from teaching high school, which is making the students do something, so solve this yourself, while I desperately get my shit together. Okay, I'm just going to look for my printout. I put it somewhere. So, I didn't bring it in? Was I holding it when I saw you? No, I thought I was. What? Where is it? No. Did I leave it in my office? Whatever. Oh, that's so me. Anyway, this one's more typical. Right, so we know how to take the derivative of a sinusoid. I assume, besties. Where's my mouse? Here it is. Oh, great. It's frozen. Mouse? Mouse? No. Nah, the mouse doesn't show up. You know what? Screw it. We'll finish the lecture when the lecture's over. Whenever that is. Oh, thank fuck. Here it is. All right. I made how many slides? That many. All right. And our break is there. Oh, we're good. We're so good. We're so back, besties. Don't worry about it. All right. Oh no, we're not so back. Yeah. Anyway. So, if we wanted to find the current through this loop, it's technically going to be a function of time, and we're assuming constant resistivity through the loop and all that jazz. Right, first of all, we have to find flux. First of all, we have to have a working computer. So first of all, we must find flux. No, stop right-clicking! Sorry, audio warning, recording watches. All right. Phi is equal to pi times 0.5 squared times 1.2 sine omega t, right? It is too hot in here. I gotta put the aircon on. This is bullcrap. It is on. I asked for it to be on. I put the button on. I didn't even move my hand! God. Okay. So now d phi dt with a negative, there's a single loop, is going to be negative. Now, is the derivative of sine minus cos? That's regular cos? Thank you. I never remember that. You will have to remember that. I have fortunately graduated from having to remember that.
The integral of sine is negative cos.
Thank you. Okay. I always forget. Anyway, 0.5 squared times 1.2 times omega times cos of omega t. Right? So that's d phi dt. And then I is equal to this thing, whatever that is, divided by 12. That's it. You just take your usual thing. Now this is what we more commonly see. We more commonly see a flux that is sinusoidal. And the reason we commonly see that is because if you take a constant area object and you rotate it constantly over time, the flux changes as cos of theta, right? Where theta is the angle this makes, well, technically the angle this normal makes with the magnetic field. Question?
What does that negative mean in front of it? Does it mean that it's like opposite to what we would usually...
It means Lenz's law. So it's there to make sure that energy is always conserved, that the induced current always opposes whatever force is causing the induction. Yeah. Yeah. There is actually also a slide specifically for that. Yes, Tarek. Sorry? There is 2 entire slides on it, or 3 entire slides on it. I will explain it. The reason there's a negative sign in there is an entire learning outcome. So hold on to that thought. And I did also decide to teach this. But before we get there, I have no idea if this will show up. But sometimes you are asked for the average of a sinusoid. Okay? Sometimes you are asked for like the average current or the average voltage for something that is varying sinusoidally. If that is the case, it's the root mean squared value, which is the square root of the amplitude. If that ever shows up. I actually don't know if it does. But just keep that one in mind. I hadn't put in a yellow slide in for forever, so I was getting weirded out. Okay, so I just put one in. All right. So, armed with our level of knowledge, may we, and now this is an open poll, so you can again go to physics, so go to, yeah, no, I accidentally closed it. I'll open it again. We'll click repoll. We'll click repoll. Yeah! Okay, good. Go to echopoll.au. And then the login code is physicsgang. And can anyone offer why it goes slow through the tube? Now, I haven't taught you all of it yet. But I've taught you a little bit of it, and I want to see if you can connect what we've just learned to what we are now observing through the magic of tube. I'll wait until we get a couple of responses. Why is it slow falling? It's got to do with induction, of course. It must, right? But why? What's changing? Is there a change in flux? This magnet is constant. This area is constant. How can there be a change in flux, and therefore an induced current, if the magnet is constant and the area is constant? The flux seems like it's constant, right? Well, wait like 1 minute. This is the quietest I've been in my entire life. Whatever. What do we say? Did I close it?
Yeah.
I'm so sorry, everyone. Well, what were you going to say?
As the magnet falls, there's a change in magnetic field, so therefore there's a flux induced and therefore there's a current induced.
Correct. It must.
Stop the magnetic flux from changing.
Exactly correct. So what we've learned up until now is that there must be some kind of induced current. Now what I want you to picture is as this magnet falls, technically the flux from the magnet's perspective isn't changing, but each different part of this tube is experiencing a change in flux. For the bottom part of the tube, as the magnet approaches, the flux is increasing. And for the top part of the tube, as the magnet retreats, the flux is decreasing because of proximity to magnet. Remember, the magnetic field strength drops off over distance. And so you're entirely correct. There must be an induced current. And what there is there is an induced current directly above the magnet, and there is another induced current directly below the magnet, each of which, for some reason that we do not know yet, opposes the motion of the magnet. So there is a change in flux by virtue of different parts of this tube experiencing different parts of the magnet. Question?
Does that mean if you drop the magnet down and hold a magnet next to it, the metal, like the aluminium, becomes magnetized at certain points, like just above and just below?
Well, it is magnetized right now. It is, absolutely. So yeah, it would actually theoretically attract another magnet to it. Let's give that a try. We'll give that a try during the break. We'll hold another magnet next to it. Because you're right? The way it slows down the magnet, it must be that the currents generated are themselves magnetic and slow down this magnet. And wouldn't it be cool if there was a law that told us about how that works? Yes, question.
Iron conductors have a low resistance, right?
Correct.
So why aren't you being electrocuted like
Because the current's going around itself in a circle. It's not going to me. And also the magnitude of the induced current's quite low, right? But also, it would have to short through me if I were to get electrocuted. So if I were to like make a giant loop and then complete the loop myself, then yeah, that'd be unpleasant. But luckily, it's not happening to me. But it will get warm, actually. It will warm up. That's how induction cooktops work, by the way. Anyway, so this is it. Oh, question, sorry.
Does the same law work with speeding up things using light?
Yes. So actually this is exactly the law, right? So basically, actually I could have phrased this way better. So I will try and phrase this way better next time. But magnetic acceleration is exactly the same thing because essentially all metal objects do not like to be moving relative to a magnet. And that could mean if you get a magnet or magnetic field moving, the object tries to come along with it. That's how magnetic braking works as well, right? But let's go Lenz's law from a phenomenological perspective. The direction of the induced currents will always be whatever direction opposes the change in flux, or, and this is the same thing, it's just another way of thinking about it, whatever direction will cause an opposition to the motion that's causing a change in flux. So as this magnet falls, the direction of current below the magnet is whatever will push away the magnet. And as this magnet falls, the direction of current above the magnet is whatever direction will pull the magnet back up. Lenz's law is always acting in opposition to whatever is going on. Has anyone ever heard of a NIMBY? Not in my backyard, right? It's a political thing. Not like a political thing, but it's like people who just, have you ever tried to make a change and then people are like, no, nothing should ever change. That's Lenz's law, right? I think about my grandparents. They hate it when things happen. So does Lenz's law. Lenz's law tells us that the induced current is whatever it is to stop this business from occurring. How dare things happen? Things must never happen. That is the idea behind Lenz's law. Now, you can apply that in several different ways. That's what we're going to do. Okay, we're going to use Lenz's law to figure out why current is induced in a certain direction. And the first thing I want to go through is how do you determine the direction of current if you know what the magnet should look like, right? So here's an important thing that you need to be able to do, all right? If, let's say for example, I had a big piece of metal, right? And I had a magnet, North Pole here, South Pole here, and this magnet was approaching the metal. The metal is not okay with this because of Lenz's law. It will induce a current. Now, if I were the metal, and I were to induce my own current such that I also behave like a magnet, and I want to stop this magnet from coming, which end of the induced magnet is going to be the North Pole? Is it going to be the right-hand side? The North Pole is going to be here, and the South Pole is going to be here. So first thing when you see a problem is, what magnet would stop this foolishness? What magnet would cease this motion? And then you have to ask yourself, okay, if that magnet was a flux line or a magnetic field line, I just say flux line because it sounds cooler, right? What direction would it point? That way. Hopefully we remember that. Hopefully you remember that a magnetic field line comes out of the North Pole, goes into the South Pole. So you could say, well, this piece of metal is generating a magnetic field that looks like this. That's what we're saying. That this piece of metal generates a magnetic field that looks like this because we know what magnet it would create, and we must therefore be able to determine the direction of the magnetic field by just turning the magnet that we're imagining into a magnetic field. But we also know the right-hand grip rule. And we know that a current going in a circle generates a magnet going in a straight line. So we would put our thumb in the direction of the magnetic field. And we would realize that if we wanted to have a magnetic field going this way, we would need to have a current that goes that way, right? Goes down on the front and it goes up on the back. And therefore, through this logical thinking process, we could induce, hello, not only could we induce hello, but we could induce that if this magnet were approaching like this, the induced current would be that way. Now, this is a thing that you should practice on your own, right? Step 1, imagine what magnet would stop this. Step 2, convert it to a flux line. Step 3, right-hand rule it. You've always got a 50-50 chance of getting it right, so I wouldn't feel too bad. But we are going to practice this a bit, okay? And that's how I teach my high school students to visualize this sort of thing. The second way to do it, if in circumstances where it does not appear conducive to you to imagine a magnet, you can just literally draw 3 diagrams. I call this before, after, therefore. It's pretty easy. So let's say, for example, I have a piece of metal here, and it's chilling out, just having a time, and then some horrible person turns on a magnetic field going into the page. What is the direction of the induced current? Well, let's figure it out using this, right? I mean, it was a rhetorical question, but good on you, right? Yes. Well, we'll see. The magnetic field has to be out of the page. So, step 1, draw the system before the change. It was a regular-ass piece of metal. Step 2, draw the system after the change. It's a piece of metal, but now there's a magnetic field going into it. Therefore, now, Lenz's law is going to tell us that this piece of metal that has a magnetic field line going into it now, it wants things to be like it was before. That's Lenz's law. So it's going to generate its own magnetic field line to cancel out this change. If it generates its own magnetic field line, which way is that magnetic field line going? Out of the page, right? To cancel out the end of the page. So it's generating its own magnetic field line going out of the page. Cool? It's generating its own magnetic field line going out of the page. And therefore, if it's generating a magnetic field line going out of the page, we use our right-hand grip rule to determine that the current is that way. And therefore, in a question where we started out with a piece of metal with no magnetism, hi, physics? Oh, hi, Peter. Sorry. That's my PhD supervisor. And boss, right? In a system where we started with a... He already thinks I'm an idiot. In a positive way, but I have a reputation of being a little bit of a person. We had our piece of metal and it had no magnetic field going through it. And when you turned on the magnetic field, it induced a current going that way. How we figured it out is we drew it before the change, we draw it after the change, and we say, well, therefore, the induced current will be whatever makes this look more like that. Right? That's what it does. It opposes change. So let's look at an example of a falling magnet, this system here, right? With the magnet that goes into the tube. And I want you to think, let's say we have our magnet right here, right? This is the magnet, and we have to put a polarity on it. So let's say it's north on the bottom and south on the top, and it's moving down, right? It's going down. What direction does the current circulate above? And what direction does the current circulate below the magnet? This is what we want to figure out. So, we're not going to do it before, after, therefore. We're going to do the first one. We're going to imagine some magnets. Okay? So, stay. Good. Okay. So, step 1. There is a generated magnet below and a generated magnet above the actual magnet. The magnet below, what is the pole on the top? If the magnet below, this magnet has which pole on its top-hand side if it's trying to repel that magnet? North. Now, the magnet on the top It's trying to attract that magnet back. So which pole is on its bottom? Also north. Right? It's trying to attract that back. Because the two induced magnets are trying to stop that yellow magnet from moving. Question?
So, the yellow magnet is falling through the tube, right?
Yes.
So, like, the induced magnetism would try to oppose the change.
Correct.
Wouldn't it try to repel the magnet?
Yes, that's what's happening. So the bottom one, it's trying to oppose the motion of the magnet. So the bottom one is trying to repel the magnet. It's a north pole facing the north pole of the magnet. The top one is trying to pull the magnet back up. Because it's trying to oppose the motion of the magnet. Yes?
Does that mean that there's a different current below and a different current?
Exactly! And that's why I'm not getting electrocuted, because it cancels out. Right? And that's exactly correct. Right? There's no net current through this thing. Because they're canceling. That's exactly true. That's exactly true. Right? And that's why, excellent. That's why you can't just throw a magnet through a solenoid and generate electricity, because the two sides cancel out. Right? Yeah. Anyway, great. So, sorry, got too excited there. I'm so glad that wasn't when my supervisor walked in. So we replace these with flux lines, right? So we replace this with a flux line going up. Question?
But when the magnet would just enter the tube...
Yes. Yeah, when the magnet just enters and just exits, there is a net current. That is correct. Yes. And technically, there is a net current for any point besides it exactly in the middle, because there's slightly more metal on one side than the other. But functionally, it is far, 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 far less than actual generators. But yes, you're thinking about the exact right way. Anyway, those flux lines point, one points up, one points down. We use our hand. So thumb points down, which means the current goes this way. And our thumb points up, which means the other current goes this way. That's how you do that sort of question. Does it show up? Probably not. Tarek? Yes. So, something we learned sometime, and I don't remember when, is the right-hand grip rule, which generally tells us it's a curl rule, right? If there is a circular current, it creates a magnetic field in a straight line. When your fingers curl in a certain direction using your right hand, the way your fingers go, that is the direction of the current that produces a magnetic field in the direction of your thumb. So from here, we've got the magnetic field direction first. So for example, the bottom one. I want a magnetic field pointing up. The one at the bottom, the one at the bottom. I want a magnetic field pointing up, and so my fingers have to go this way. So that's the direction of current. So what I do, like imagine arrows drawn on your fingertips and your thumb tip. It's annoying, but is that a thumbs up because you get it, or thumbs up because you're trying it out? So I like this one. Yes, question?
So for like a charged particle in a magnetic field, we use the Fleming's, right?
Yeah. So for a charged particle, so for things in which it's not going circles, use the right hand normal rule. And for a thing where there is a circle, use the right hand grip rule. That's the only way I think about it. Question?
So the induced magnet opposes the falling of the first magnet.
Yes.
Wouldn't the first magnet also induce a current to oppose?
So you're saying, like, is there a second order effect is what you're asking? Like, does the induced, of course there's going to be second order effects, right? The actual answer is that we don't think that far ahead, right? But you're right, because this is going to be generated out of nowhere, and so the other part of the metal is going to be like, hey, what the hell's going on here? I'm generating my own current to oppose that, and so on and so on and so on, right? Absolutely is that going to happen. We won't think that much. Actually, all of these are technically called eddy currents. Anytime there is an induced current that is just a circle around a piece of metal, it's an eddy current, right? Eddy currents are just induced currents that don't go anywhere. They're just kind of... So yeah, it would create like sub-spirals and stuff, right? And the wonderful thing about physics is that we love ignoring stuff like that. We don't have time to do that one. All right. That's where the minus sign came from. All right? The negative sign there is the indication, and this doesn't make any sense to you right now because we don't have any vectors, right? So it's like, well, why is, like, minus sign doesn't indicate anything. But when you do the vector form of this, which I will show you, but we won't do, right? Then that negative sign is telling you that the generated electric field in an EMF is technically in opposition to the change in flux. That's what the negative sign is supposed to mean. It'll make more sense once you see the differential form of this equation, which is much better. But it's not the one I'm supposed to teach you, so sorry. And what this means, by the way, is when something gains electrical energy, something else has to lose energy. That's why generators need input. That's why the wind turbine, when you spin the big metal, because you're just spinning a coil in a magnetic field, right? So change in flux, so it's generating an EMF. That's why there has to be wind still, right? It's why when you go to the coal plant, you have to keep shoveling the coal. I don't know if they shovel it anymore, but that's why you continuously have to put energy into a generator to get electricity out. Because whenever you generate electricity, there is always some sort of force opposing whatever motion causes the energy generation, right? If you were, for example, to use this hand generator, right? You feel a resistance because the current you're generating fights you. And that fight is doing negative work on you. You are losing energy by virtue of generating energy. Now, there's no questions on that, so I'd rather spend like 3 hours talking about the fun implications of that, but I have to prepare you for things. Speaking of preparing you for things, here's a potentially arbitrary object. Why has Tom brought this up? Okay. So this is a thing, we don't do inductance, do you? Does anyone do electrical engineering? Goated. All right, so you guys done complex circuits yet? Like AC circuits and stuff? Okay. When you do, yeah? Nice, let's go. So solenoids have very interesting transient properties. Technically, now that we're doing time-changing objects, because this is the first time we're actually not assuming steady state, right? This is the first time we're doing derivatives over time. This is the first time we care about temporal variations. And that actually has huge implications for how capacitors and inductors, or coils, work. And we are not going to look at it at all. But just as soon as you see a capacitor, if there's any time derivative on it, forget whatever you were thinking. Same for coils, technically, all right? But anyway, if you have two coils wrapped around each other, typically speaking, the flux generated by one of the coils is the flux experienced by the other coil most of the time. So to find the flux generated by the first coil, B equals mu naught I N over L. You learn this next week in your lab as well. And that means that the flux is the magnetic field times the area of the first coil. And then that amount of flux is experienced by the second coil. Keep this in mind. May be relevant later. Okay? You know how to calculate the flux generated by a coil. It's just N times the flux generated by one of the loops, which mu naught I N over L. Anyway, and this is just a thing I'm just saying for fun. Now, much to my disappointment, there are myriad technologies, i.e. damn near everything that's electrical, that works because of this. But if I were a strategic person focused on preparing you to succeed in this course, it would be bad of me to teach you or to focus extensively on things that are merely cool and not accessible. And I want you to know that my heart breaks for having to do this. But for example, that's how a transformer works. Who's charging something right now? No one. Okay, good. Who has charged something before? What does the thing you plug in look like? It's like a brick, right? Why is it so brick? Why is there always a brick involved, right? Whenever you charge something. It's because it's a transformer. Transformers are how we change voltage, right? And the mechanism thereby is an entire 20-minute lecture. The maths is very easy, but it is not a learning outcome of this course. I just want to say that two solenoids, one of which generates magnetic flux and one of which experiences the magnetic flux, is the main way we get changes in voltage. Because if you change how many coils are in the first one versus the second one, you can just change the voltage, literally by the ratio of coils, right? So if the ratio of coils in the first half is twice the coils in the second half, the voltage becomes half or double. One of the two, I forget. It's probably half. It's half? Is it double?
Yeah, because you usually want more voltage to the output, which is to the mobile phone.
No. Well, this might be a step-down transformer. We don't know, right? Literally, it's a 10-second Google away and I already forgot, right? But importantly, this is how nearly all voltage transformers work. That's what the word transformer means. It's transforming the voltage from one thing into another. It's why we use AC. Because remember, it's changing flux, right, that enables all of this to happen. And so we use AC current that is varying with time, and more specifically current that is sinusoidally varying with time, because you can derivative it as much as you want and it's always the same shape, right? The derivative of cos is sine is cos is sine is cos is sine is cos is sine, right? And that's why we use sinusoids in electricity, because you can chuck them into Faraday's law, and yes, if the initial current was a sinusoid, the induced current in the second half of that transformer will be a cosinusoid, but still the same shape, right? And then you can kick it into another transformer, you can kick it into another Faraday's law thing, and so on and so on and so on. That's why AC is, like, sinusoids are basically the greatest mathematical function of all time, because they are infinitely differentiable. Yes?
Wait, so does this offset the current and the voltage, so it like lags it, it's like...
Correct. There is actually a 90-degree phase delay when you use one of these. Exactly correct. But again, we're not dealing with we're not dealing with interesting transient behavior in this course. But yes, absolutely, right? And that's why they induce complex numbers in these sort of things, because you need to represent the phase change somehow. But I'm getting far ahead of myself. Shout out to a book called The Art of Electronics. That is just my favorite book. Torrent it or buy it. I have a copy. It's literally, if you're interested in anything to do with electronics, that's the greatest book of all time, right? The Art of Electronics. I lent it to someone in undergrad and they spilt coffee all over it. I got it for my birthday. I asked for it for my birthday from my parents. Yes, Tarek. No, go ahead. I was telling random shit.
I was just wondering, like, in terms of like a book that supplements materials.
Yeah.
There was like the physics textbook that they kind of got a lot of from 1A. Is that also?
Yeah, I use the same physics textbook. So the same physics textbook for 1A, that's what I double check my lectures against, right? Because to be quite honest, before having taught this, I'd forgotten all of it. I mean, I knew how to do like the maths and stuff, but I was like, oh, what's dipole moment again? And so I used the textbook to figure that out. So I would recommend it. The textbook explains things far more thoroughly than I do, because it has far more time and far more space. Each lecture learning outcome has a textbook reference on it. If you go on the week 1, week 2, week 3 pages on Moodle, they have textbook references. The textbook's decent. There are a bunch of copies in room 201A, which is above the first year labs, that no one keeps track of. Okay? Just saying. We have like 30 copies. Now, the editions might not be up to date, but like, come on, it's physics from the 1800s. It doesn't change that much. Now, before we go on our break, I want you to think of what you're going to be learning next week. Because we have just finally seen some sort of electric and magnetic interaction, but it was unfortunately confined to circuitry, right? It was confined to electric field and, it wasn't. It was confined to EMF, which is some bullcrap voltage, sort of, and a change in flux. But there has to be a more fundamental relationship, right? There must be some more fundamental relationship between electric fields and magnetic fields, right? And of course there is. This is called the Maxwell-Faraday equation. It is not needed. You do not need to know this, okay? But I just want to show you, this is what we're basing it on, all right? This is our relationship between electricity and magnetism. What I want you to notice is that the electricity's spatial variation, kind of, that's what this grad gives us. Remember, the triangle is dx, dy, dz, right? And triangle cross E, don't worry about it, but it's something space related, all right? Something spatial, is the time change in magnetic fields. There's this lovely, interesting relationship between spatial dimensions and temporal dimensions, and that's why the only solution to something like this is a sinusoid, something that varies in time and in space with the same equation, right? A sinusoid, if you looked at one point of it over time, it maps out a sinusoid with time. If you took a photo of it and mapped it out through space, also the same function, still a sinusoid. So the only solution, also exponentials, but we're not dealing with those right now. Those are called effervescent waves. We don't need them. The only solution to these sort of equations is sinusoids, and that's why sinusoids show up in waves, because they're the only things that kind of fit this requirement, that the spatial derivative, kinda, is equal to the temporal derivative, kinda. And I'm really hand-waving here. I'm really just making shit up. But importantly, this has an integral form, all right? And you don't need to know this, but you do know this. Because this integral form should look infinitely familiar to you. Right? Integral B dot dA, that's just flux. That's just you know, that's flux. That's literally the definition of magnetic flux. And integral E dot ds, loud. Integral E dot ds with a little circle, that implies it's an integral over a closed loop. That's what that circle over the integral means, right? That's just the voltage along a loop, right? If you integrate, so this is technically the correct definition of Faraday's law, right? It's this. And then this means EMF. That's what we take EMF to mean, right? The loop the loop integral of electric field with respect to distance along the loop, right? That's why we don't say it's a voltage between 2 points, because it's technically the loop integral of electric field with respect to distance, which has the exact same format as voltage between 2 points for a non-looping thing, right? Because unfortunately for us, in real life, can I draw this? No, God. Right, and this is just me going off script here, right? But in real life, if you had delta V equals integral loop E to ds, that's by definition 0, because the voltage between 2 points, if they're the same point, is 0, right? And this is the differentiation between EMF and actual voltage, is that EMF is this property that can be accumulated over a loop and voltage is not. It's cringe, right? But we use puny human language to express beautiful physical reality. Let me just do this. Oh, we're not doing that. I'll make a video doing that, because we need to go break. Question. 2 slides back, yeah, okay. Yeah, I'm trying. Yeah, this one?
So like over here, if we look down, like the surface integrals, the circle kind of thing is missing.
Yes.
So if the circle comes in, then E dot ds is 0.
Technically, yeah, because it's an entire loop. And it's a hand wave to say that EMF and voltage are the same thing. They're technically not, because of this integral definition. EMF is like this distribution of voltage over a loop. And voltage, as we do it, is explicitly 2 points in space that are not co-located. If they're co-located, then it's 0. But this is the limit of first year. Like we used 2 kind of non-similar but similar enough definitions, and so they have the same vibe, but they're mathematically not the same thing. And that's the problem. Yes, question?
So if you close an electric circuit and then there's current flowing, would that mean that there's a magnetic field that opposes the current flowing?
Only if there is a change in the current flowing, right?
Yeah, but as soon as you
Yes, that's why inductors take a while to ramp up.
right, okay.
Yeah, that's exactly it.
It goes both ways.
Yeah.
When you introduce magnetism, then
100% it goes both ways. 100%. That's why if you graphed current versus time through an inductor, when you close the switch, it ramps up because there's this magnetic field opposing. That's exactly correct. That's exactly why that happens. I just freaking love analog electronics for that reason, right? It's so cool. Anyway, we'll take our break. But yeah, that's exactly what's happening. Yeah, what's up? Oh, yeah. Let's do that now. Yeah. Come. You want to do it? Yeah. Come do it. You can do that, and I'm going to try and get a bunch of these experiments working. So, here you go. It's a magnet. Here's 2. That's very important. I'm going to try to get that. Everyone, especially online people, very important point that someone just raised. I got the whole voltage definition wrong. The whole voltage, it's literally me not being able to algebra, all right? But it's, you still do the same equation. It's QE equals Q drift velocity times B, and then E equals V over D. Watch this, and where V is the Hall voltage. So Hall voltage over D is equal to Q, sorry, no more Q because I canceled the Q's, VD times B. And watch this. Now you multiply both sides by D. And you get the Hall voltage is equal to V, the drift velocity, times B, times D. And some idiot like me had it over D, because he's a fool in the notes. So I'm going to post a very embarrassing announcement about that, and the fact that I literally can't multiply a letter across. Thank you very much for pointing that out. No, look, legitimately, right? My brain don't work good, right? Sorry? I just can't, I'm just not the best maths person. Well, more specifically, and this is unfortunately true, I exist in an environment that is low stakes enough that when I make these sort of mistakes, it's immediately easy to correct them because I'm not doing an exam, right? I'll level with you, when I was studying for my exams, I was way more on top of this stuff, right? I got like HDs in all my exams, all the complicated integrals. And it's like a muscle. If you don't exercise it, it's gone, right? And for me, it's, Tom, do you know how to freaking multiply? Anyway, lol. Thank you for pointing that out. I really appreciate it. I'm so stupid. What's wrong, besties? Joints. You're not old. I'm old. Right? All right. Before we go on to our next lesson, I want to show you some magic. Let's do some more tricks. All right. Observe. This is a pendulum. Oh, come on. Observe. This is a pendulum. Wow. Observe how it goes. Now, if I were to flip this switch, all of a sudden there would be a magnet here. And now I want you to remember that whenever a piece of metal moves relative to a magnet, Lenz's law is like, how dare you? And tries to stop that. So it's swinging like normal, and then as soon as I induce a magnetic field along it, it just stops, straight up. This is how electromagnetic braking works, right? It's moving, it's moving, it's moving, turn it off, oh, stops immediately, right? This one, more complicated. Excuse me. There we go. So this does anyone have a light bulb on them? Hang on, let's just try and make a spark. That'll be funnier. All right. All right, I'm gonna try and induce a spark. Ah! I do need someone to hold it down, but you'll be liable for damage. So it's not worth it. I'll just get my foot up. Hang on. All right. I got this. Go. Dang it. All right, well, clearly I'm not generating enough voltage to generate a spark, but that's what this would do, right? Because I'd be generating a change in flux, and then it will make a voltage. Yes, question?
With the one where the magnetic braking, if it was a permanent magnet, over time would it lose some of its magnetism?
Yeah, absolutely. It would lose some of its magnetization. Definitely, yes. Because the kind of domains inside that magnet would experience themselves some force from the induced magnet, and eventually it would kind of decay out the magnet. I have no idea how much and over what time, but yeah, it would kind of wear out. But relative to friction braking, it basically doesn't wear out, which is why we use it. But yes, I'm so proud of everyone with their thinking. Except for obviously me not knowing how to multiply by D. I'm so stupid. I was writing that at like, 1 a.m. So that's why. That's not why. Okay. Last lecture. Does anyone remember torque? Yes, right? R cross F. Right? The spinniness of force. Yeah? Yeah, good. All right, it's back. We're doing torque. Is this on? Yeah, it's on. All right, good stuff. Surprise! Integral time. Sorry? You don't want integrals back? You don't want? Oh, you want me to revise torque? Oh, you don't want torque back? I'm sorry. I'm very sorry. Okay. I want you to imagine, right, this pole. And what if this pole was being held at an edge and there was a force along the entire pole, maybe because it's a wire and a magnetic field. Hint, 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 okay? Let's say there was a single pivot point and there was a force all along this pole. What's the torque, right? What you'd have to do is you'd have to find the torque due to the force at this point, and at this point, and at this point, and at this point, and at this point. We integrate. It's an integral. Of course it's an integral. Of course it's an integral. So that's the first thing I want you to realize is that, and I think I made a better one here, right? Okay, hang on. We'll go back. We'll go back. Don't worry. This is actually not too bad. I'm literally preparing you for something. Sorry? No, it won't be vectors. I just put the cross product in there to be proper, but don't worry. Okay? So what you have to do is you have to infinitesimalize the force. You have to go, well, there's a little element of the rod that experiences a force dF. Now, maybe for us, heavy hint, if we have a current running through the wire, then maybe the force on that little component of the wire is going to be the current in the wire times the magnetic field along the wire times the little element of length. Maybe we're going to have to do that at some point. Hint, right? Right, this kind of infinitesimal relationship is very important. Question? No? No, okay. Something funny? All right. And so what we will say, right, is that each little element of force here contributes a torque d tau equals r dF. Now, r is the distance between, for our case, that little piece of the wire and the pivot point. So what we will do is we will set up an equation. Now, technically speaking, the proper infinitesimal integration is r cross dF. But for us, and I really should have put this in the notes. That's why I copy-pasted it. I was then meant to edit it. But again, I wrote this very late at night. That's no excuse, by the way. I'm just a little dumbass. R dF sine theta. We will only have to integrate the sine if theta somehow varies with the same variable that f varies with. But in this picture, f is always perpendicular to r, and therefore sine theta is always 1, right? Is there going to be a time where you don't have sine theta always equals to 1? That would shock me if that occurred. It would shock me greatly if that were to occur. Well, I didn't say no. I would just say it would shock me greatly if that happened. Okay? So let's try an example. All right? I have a wire, of a length L, current I, running through it. Don't ask how the current got in the wire, all right? It just did. Okay? Don't ask where the rest of the wire is. This is current going through its magic wire, okay? The pivot point is at the left end. What's the total torque on this wire? Yes?
1 second. Just like for electric fields, we had an electric dipole moment, but we have the same for magnetic fields.
Do you know what's in this lecture? Magnetic dipoles. They're exactly correct. There is exactly a magnetic dipole.
Magnets always have to exist.
Correct. You're exactly. It's like the last thing we learned today. You're exactly correct. For an electric dipole? Because we say that the electric dipole's field is in the same direction as the dipole moment, and that means that the electric field points in the same direction that the negative points to the positive. Is it the other way in chemistry? I'm sorry. I don't know. Yeah, so the reason the dipole moment is defined a certain way in physics is because of its relationship to electric field, the direction of electric field. We say the direction of dipole moment is the same direction as the direction of electric field due to a dipole. And I don't know how they define it in chemistry. I'm very sorry. But we always do this. We always have opposite definitions of these positive and negative things. I don't study chemistry, so yay. Anyway, very astute on magnetic dipole. We will get there today. So, the wire length L has a current of I running through it. The wire is perpendicular to magnetic field strength B. What's the total torque? So what we're going to do, we're going to go, all right, well, total torque, I was gentle that time. I know, sad. Tau is equal to integral R dF, right? And now let us make a definition of dF. So any little part of this rod, this little part here, right, this little part of the wire, that's experiencing a force dF. Now, first of all, we should figure out which direction that is, right? So we put our fingers going into the page, we put our thumb pointing to the right, and so the field is up. Sorry, the force is up. This is force, so dF is up, right? Again, fingers pointing into the page because that's across, thumb pointing to the right because that's the direction of current. Our palm gives us up. So that's dF. Now, if this is how you do it, if F equals BIL, then dF, presuming the others do not change, presuming B and I to be constant, which is the only reason you can do this, that's equal to BIDL. Now, of course, if I and B were not constant, you'd have to do 2. You'd chain rule it. You don't have to do that. Don't worry in this year. But you're entirely correct. You would chain rule it if we had a variation according to B and I. Like if dF, dB was non-zero, blah, 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 blah. Anyway, whatever. Point is that B and I are constant for us, and therefore we can make this assumption. And so we go, okay, well, torque is equal to the integral of R, B, I, dL, where R is the position, right, of whatever point of the wire we're talking about, R, right? So what we should say is this is equal to R, B, I, would you say over? dr, right? We have to make our two spatial variables the same, right? Because R here is talking about the portion of the length of the wire we have, and dr is a little bit more of the wire. They are the same variable. And we, of course, mean this is from R equals 0 to R equals L, the full length of the wire. Now, of course, we have implicitly in here that sine theta equals 1, right, because they're perpendicular to each other at all times. And then this becomes torque is equal to BI R squared over 2, R equals 0, R equals L. I hope I didn't screw up that integral, everyone. And that's equal to BIL squared on 2. Right? Which is literally just the torque if you assumed the force acted through the center, by the way. Because just the length would be L over 2. Yes?
You can also do the integral of FDR, right?
Yes, so you can also do the integral of FDR. The reason that that's more complicated is because, well, technically because of the direction, but also because then getting the length element of the wire is a bit more difficult because dr is technically the pivot point. Anyway, the point is I tried it and I couldn't hack it. And so it doesn't work as nicely. But yes, I also did try that. And I was like, why isn't this working? And then I gave up and did this. So I'm trying to think of why it didn't work aside from I suck. But I know from experience, it don't go so nice. Or at least I couldn't get it going in a way that I felt like I actually was doing it properly instead of just ass-pulling it to be the right answer, right? Which was the main thing. But yes, that should theoretically work because you should get R squared on 2 anyway, right? Like both ways. Or you should get distance squared over 2, like length squared over 2 is what you want to get. And I think the reason it works in this case is because the force is constant. And then perhaps it wouldn't work if the force wasn't constant, right? That's my thinking. But again, I'm just spitballing here. Don't worry about it too much. I mean, you can if you want to. But it's a good, like we're brushing up against the limitations of all the simplifying assumptions we've made, which is good. That's how we know we're at a good level of thought for the course, right? Is that, Tom, this falls apart when you think about it too much. Yes, that's the correct level to think about it, right? Like, be aware of these limitations. That's very good. You're going to be very prepared for second year. This is a motor. This is a DC motor. I am going... Oh, should I just plug it into a battery? Yeah, let's do it anyway. That's okay. We're gonna... Okay. Famous last words. All right. No. We got this. So I'm gonna plug... What am I... It's stuck. All right. Oh, wait. No. That one's gonna... Anyway. So this is supposed to be a DC motor. So... It's plugged in good via a doodad. We'll use this. Is this a thicker wire? Yeah, we're using this thicker wire. I'm not trusting. So the idea is, oh, this doesn't have an alligator clip. This has an alligator clip. I don't need an alligator clip. Hang on. The idea is that it's possible to make a motor. Like electricity in, it goes, it spins. And the idea is that all you need, if I die, I want you all to know it's because I care.
Literally your last day.
Yeah. Okay. Okay, I'll get it spinning. Ah! It worked! Okay, hang on. Okay. Ah! What's that? Whoop. Hang on, you have to get it from a good start point. DC motors are really finicky like this. Especially shitty ones like this. Oh my God! It go! Right? Through the power of magnetism, we achieve motion. Woo! The reason is, by the way, right, is because this motor has an inconsistent torque. The torque on this motor depends on the orientation of the coil relative to the magnetic field, as we are about to derive. And if you have it starting in a position with zero torque, it doesn't go. But if you have it starting in a position with maximum torque, it has enough momentum to cross that zero torque threshold. Because the torque on a single coil DC motor goes with sine theta. Right? So I start at the max torque condition and... Come on! You worked before. Okay, well, you all saw it working earlier. Have I literally just, like, destroyed the battery? Yes. Yeah. Oh, I'm glad you know what to Ah! That's the best. All right. So, a simplified version of it is this. Okay? We've got this wire, this loop of wire, and what is present is a magnetic field through this wire. Okay, there's a magnetic field here, right? That's what it looks like down here. You can come take a look at it later if you want, right? But what we need to perceive is that there is a loop of wire, a coil of wire, and that coil of wire is present in a magnetic field. And so what's going to happen is when you run a current along this wire, we don't have to think about change in flux. Don't worry, there's no flux anymore, okay? Although, technically, okay, don't think about it, but you could put flux in this if you wanted to, right? Each side of the wire in the magnetic field is going to experience a force. And if you do the maths, this side will experience a force this way, and this side will experience a force this way, if you do the right-hand palm rule. And what you'll get is that this motor, by virtue of the current going this way on one side and this way on the other side, is going to experience no net force, but it will experience a net torque, right? So I'll show you. I'll try and show you. Right? Let's find an expression for the torque on a loop in a magnetic field. Yes?
Will like the top ends of that also be facing the door? Will be facing the door?
Oh shit! I broke it. Sorry. Yes. But each side, as if we do the maths on it, what will happen is these two sides will cancel out, and these two sides will cancel out with each other, and the net torque is only provided by the ends. The reason it is, if you imagine a magnetic field going into the page, right? These and these provide forces, right? But the force on this wire is down, and the force on this wire is up. And they don't apply any spin, because we are only looking at torque about this axis, right? You're right, there is this kind of like lifting torque from these two wires, right? There is absolutely a torque from these two wires, but because we've got this pivot point and it can only rotate this way, the only torque that we get is these two sides.
The top and the bottom cancel each other.
Correct. But they could generate a torque, but there's no axis for them to rotate around. And so yes, there's technically a torque, but we don't think about it because it's not useful to us. Also, I can't believe I broke it, lol. It spontaneously broke. That's what we'll tell Tom anyway. So let's try and derive it. Let's try and derive the torque. All right, what I want to do is derive the torque on this wire, right? And first things first, we're just going to consider the sides, these two sides, okay? So let's consider that, the magnetic field, this is side A. Oh, that's really ugly in color, isn't it? Let's consider this side is A, so this is the A side, and these are the B sides, right? So these are the B sides, right? Now, the force on wire A, right? It's going across the magnetic field. The magnetic field in this case is pointing straight up. I'll draw it with another color. I'll draw it with another color. I won't draw it with another color. Magnetic field going up. I'm sorry. Yes? Oh, you're doing right-hand palm roll. Anyway, the magnetic field's going up. The current, in our case, was going this way. So we had current going this way. We have magnetic field going up. Right? So we can find the direction of force. Right? It's going to be palm up, thumb that way. It's out of the page. Right? And the other one is into the page. Right? So importantly, we're going to get on these two opposite sides, because the loop is like this in the picture. On these two opposite sides, we get an opposite directional force. Now, we want to find the magnitude of that. So the force on each of these wires is BIL, which in our case is BIA, A the length of the wire, right? A the length of the side of the wire that we care about. Now, the torque from that force is force times distance, right? Now the distance, the axial distance, is half of B, right? It's half of B. So the torque, due to one wire, is BIA, the force, times B over 2, right? Is it? That's the maximum torque, right? Remember, if this wire is experiencing a force into the page, and this wire is experiencing a force out of the page, it will stop rotating when it becomes horizontal, right? Because one wire is trying to go this way, one wire is trying to go that way, and so actually the force is also dependent on the angle between the wire and the magnetic field, right? Or more specifically, between the coil and the magnetic field. So we'll call it BIA sine theta, right? Here, theta is the angle between I have this on another page. It's the angle between, yes, well, technically the normal to the plane of the coil, right? The normal to the plane of the coil and the B field.
Yeah, because it's maximum when theta is equal to
90. Yeah. So, I think I've either done sine. It depends on the definition, right? If you define it relative to the coil itself, it's cos. Question.
Will the normal of the plane of the coil be like
It's perpendicular to the actual coil.
it's perpendicular?
Yeah.
So it'll be like the dipole moment?
That's exactly what we're about to do. That's exactly what we're about to do. That's 100% it. Yeah, exactly. We're going to define it as a dipole moment, but we'll get there. We'll get there, right? That's the torque from one of the wires. So for the other wire, it's the same. We add it together. And so the torque is now BI AB sine theta, which is B times the area of the coil, right? That's what A times B is. It's a rectangle, right? Times I times sine theta. Now, let's quickly go to the next slide and see if I'm not a dumbass. Oh, thank fuck. I'm so glad it's sine theta. Because it's two wires. This one was A over 2, and this one goes with, B over 2. And this one also goes with B over 2. When you add them together, it's just B. Yeah, good question. Right? This is why I like to print out my notes to double check that I'm using definitions consistent with what I'm about to define for you. Luckily this time, I guessed how I define it correctly. That the torque on a loop of wire is B, the magnetic field strength through the wire, the magnetic field strength through the coil, times I, the current in amps, times A, the area of the coil, times sine of theta, where theta is the area, theta is the angle between the normal to the coil, so the perpendicular of the coil, and the magnetic field. And the exact reason we define it like this is because it slots very well into our definition of a magnetic dipole, where when we picture a magnetic dipole, as we will see later, we imagine it as having a direction perpendicular to the area that the current sweeps out. So that's a thing. Now, if I were to be honest, I would dedicate 2 lectures to motors and generators and the various torques thereof. But I had to be strategic based on what kind of assessments and stuff you'll get. I want to say, though, we just did that derivation for a rectangle. Is the answer valid for non-rectangles? Yes. Prove it? No, I refuse. It is valid, though. All right? Technically, torque is I, current, times B cross A, where B is the magnetic field as a vector, and A is the vector form of the area, right? And if you don't do vector areas, don't worry about it. It's just BA sine theta, okay? It's just BA sine theta for us. I mean the normal to the area, right? But when you represent an area with a vector, you represent it with a vector that is in the direction of the normal that has a size equal to the area, or size representative of the area. It's so stupid. Yeah, it's not stupid, but it's a weird thing, right? But yes, because A is a vector that represents the area, right? And has direction perpendicular to the area. I love math 1141. Yeah, because you do the parallelogram, you do B, but then what about a circle, right? I know. The answer is don't worry about it. Don't worry about it, okay? It's BIA sine theta. It's always BIA sine theta, even if it's not a rectangle, even if you don't do vectors, it's BIA sine theta. Don't worry about it. I want you to think in my last lecture. I feel so bad. But then the question is, why does it go in a circle? Because the torque, right? The torque on this wire, all it's doing is trying to force the wire into this position, right? It starts out with maximum torque, and then it ends up with minimum torque. Or it could start out like this and end up like this, right? Depending on your orientation and magnetic field. But there's nothing to tell the coil to keep going. In fact, if the coil's equilibrium position was vertical like this, right? And you started with the coil like this, when you turn it on, the coil would go all the way to the vertical. It would have enough momentum to pass through, but the direction of torque would immediately be opposite. Because this wire always wants to go up, and this wire always wants to go down. And so if the wire was like this, it would go like that. If it was on this side, it would correct itself to vertical as well. So what we should be getting is an oscillation. It should be oscillating around the vertical. Nothing? All right. So what we must do is we must change the direction of the current, right? Every time the coil approaches the vertical, we have to flip the direction of the current so that now the other side wants to be on top. And then we flip the direction of the current so now the other side wants to be on the top. And how we do this is with this thing called a split ring commutator. Come on in, bestie. Hello. And so, do I have a better picture of it? Yes. Right? What it does, you can come take a look at it if you want, right? It's two rings. They've got a split down the middle. You can come see it here if you'd like, right? And each of these rings is half of a connection, and by the time the whole thing rotates, the direction of current swaps because it changes which side is connected to which. So let's say, for example, right, this side is positive, this side is negative, this end of the wire is called wire A, this end of the wire is called wire B. We have heaps of time, right? Yeah, we have time. We have time. Okay. We'll go to dipoles very soon, right? Now, by the time this whole thing rotates, right, wire B, which was negative, has moved to the positive side and is now in contact with the positive electrode. So wire B becomes positive, and wire A becomes negative. It's kind of confusing. It's not that assessed. It's worth an entire lecture. I just want to tell you that we've thought of these things, but unfortunately they're not what we're being assessed on. Question?
I mean, I may be wrong, but it seems like this is violating conservation of energy or something.
Ah, is it? So, you would be entirely correct, except for this notion called back EMF that we will not go into. But believe me, the notion is correct. Tom, the system as you've described it appears to violate conservation of energy. Correct. Therefore, there must be some sort of mechanism we have not yet discussed that ensures energy is not violated. That is correct. What happens is as the motor moves, it induces a current that opposes its own motion and reduces the electrical energy in the signal. But we don't do it, unfortunately. It's called back EMF, and you're entirely correct. Right? Very good thinking. And this lesson is really where we run into the limitations of I had to pick things to say. And there's only certain things that are assessed. So here's the final thing that's relevant for some reason. And it is magnetic dipoles. Right? Any circulating current, or even any charge moving in a circle, which as something will attest to you is a very incorrect classical way of picturing electrons, but still valid for our purposes. Any circulating current can experience a torque when placed in a magnetic field. So for example, in an incorrect classical perspective, which we will still use, if an electron was orbiting a nucleus and you applied a magnetic field to it, it should experience a torque. It should align with the magnetic field. That's how magnetic resonance imagery works, by the way. It aligns the dipoles of various atoms with an external electric field. This is worthy of an entire lecture in and of itself. It does not get an entire lecture in and of itself because this is it, right? But we have this property called magnetic moment. It is the magnetic version of dipole moment. It is actually not that difficult to calculate, and it is a thing you should know about. It has far more wide-reaching implications than what we are going to discuss today, because we have 20 minutes and you have assessments. Okay? But it's called magnetic moment, M with a hat. It's M with a direction, because it is equal to something. Right? Now, let me tell you, in terms of dipole approximations, the magnetic dipole approximation, i.e. pretending things are magnetic dipoles, is one of the most useful approximations you will ever make in the design of, let's say, for example, biomedical devices, right? Because every single, not every single atom, but damn near every single thing can be approximated as a magnetic dipole. So magnetic resonance imagery, MRI, approximates various atoms in your head, i.e. hydrocarbons and the presence thereof of various different hydrocarbons and the subparts of hydrocarbons, blah, 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 blah. It approximates them all as dipoles. And it just says, well, let's assume these are dipoles and let's kick them with a magnetic field and see what happens, right? Because And I don't know why. Okay, look. In the picture that I illegally downloaded, it says M. In some form of examination, heavy wink, it's mu. Okay? Mu, M. Mu is just Greek M. Okay? I know there's a lot of people like, Tom, that looks like the letter U. I'm like, well, it's M. All right? Yes?
Should that be a cross between I and A to get a perpendicular?
No. There is no cross this time. Because mu has the same direction as A. A here being already the normal vector of itself.
Oh, okay.
So A here, this A is already the normal vector
To the surface.
to the surface. Because whenever you see an area that is a vector, the direction is the normal direction.
Oh, okay, yeah.
Because areas can't have a direction unless the direction is normal to that area. It's a very annoying math thing. But yes, you good. But there will be a cross product. Don't worry. Okay, I promise you there's a cross product. Question.
If you were to change the direction of current in this loop, then M would be down.
Yes, exactly correct. But also, you could picture, so the question was, if you change the direction of current, does M flip? Yeah. But similarly, if you had the current going this way and you flipped it upside down, the current's going the other way, right? Like you could just literally like imagine you're flipping the coil. That's exactly what that is. And we call that, I've got a whole rant, I'm not going to go into it, but there's like parallel, anti-parallel, there's a lot of stuff. There's energy taken, it takes a certain amount of energy to flip a dipole, and that's how magnetic resonance works, is because I have so much rant, anyway.
So like in like one parallel orientation, would energy be like max, and then the other one?
Yes!
Like the negative?
Yes, exactly correct. And then the work done between those two is dependent on the magnitude of the dipole, and then you can measure exactly how much energy something absorbs when you shove a magnetic field at it, and that's how you can figure out what its dipole moment is, and that's how magnetic resonance imagery works. Is you basically take a dipole and you're like, would you like this much energy? And the dipole's like, no, thank you. And they're like, okay, would you like this much energy? And the dipole is like, yes. And you're like, okay. Therefore, the dipole moment must be this, because it took exactly this much energy. And actually, let's look at that. Fuck. Let's look at it next. Sorry. The torque on a dipole, it's mu cross B, right? Where mu, if you remember, was IA in a classical sense, in a non-vector sense, right? But it's technically IA, and why was it lowercase I? Because it was a small thing, and we were pretending it was like lowercase I is like a current when it's not really in a wire, it's just kind of a little charge moving around in a circle, right? It still means current. Also, importantly, completely unrelated, in a test, if you ever had to write I in Moodle, you have to put a percentage in front of it first, okay? Don't ask me how that's going to come in handy, but it is, okay? It's got to be percent I. It's just stupid Moodle. It's just Moodle. Yeah?
When writing current in an expression, you have to write percent capital I, or only lower.
Only lowercase I, because otherwise it thinks it's the square root of negative 1. We need more letters. Anyway, so torques experience a dipole. Dipoles experience a torque. Not torques experience a dipole. Dipoles experience a torque. It's mu cross B, which is literally just, right? That's I. Come on, let me write. Literally, if mu were equal to whatever, we're doing it on this side now. If mu were equal to IA, right, and we'll just get rid of the directions now, then torque is IAB sine theta, where theta is the angle between A and B. It's the exact same thing we just did for a coil of wire, but it's for a magnetic dipole. Anyway, this is the other thing you need to know. Oh, no, we're not doing a calculation. We don't have time. All right. This is the relevant one. The work done on a dipole. Now, I want you to remember that we at some point in the past, not much time, we derived the force, the torque, the energy, there we go, we did it in that order too, on a electric dipole. And we did the integral of tau d theta, and we did some maths, and we came up with a lovely expression that was P E cos theta, I think. I forget. Minus? Oh, 1 minus cos theta. Yeah. Correct. It's a similar expression here. Similar, not the same, right? But it is still integral of torque, right? And so the work done on a magnetic dipole can be derived, but we won't do it for time considerations. My apologies. All right? But it's more effort because vectors. Because it's a cross product and it's just annoying. So instead, it's just this. It's delta, the change in energy from one orientation of a dipole to another is the change in the dot product of mu and b in one orientation versus another, or more specifically, it's the change in mu b cos theta, which is probably mu b cos theta 1 minus cos theta 2, which in some case will be 1 minus cos theta if it goes to a certain value, right? Look, just do literally the practice question that involves a dipole. This is the work done on a dipole. This is a change in energy of a dipole. Yes?
In quiz 3, this formula appears, it's really weird and it was freaking me out. And then it also says to put it over half kBt.
Oh, yeah. That kBt business is, I hate that question. Maybe that's a good question to ask in our revision session. Or for someone to ask. Sorry? It's all it's trying to tell you is that it wants the potential energy of the dipole to be equal to kBt over 2 or something. And then for you just make the concatenation delta U equals kBt over 2, and then you don't think about it anymore. You don't actually do any thermodynamics. It's just the question telling you that the relevant energy here is kBt over 2. How do I achieve that energy? They're not asking you why the hell does kBt over 2 matter. They're not even asking you what Boltzmann's constant is. But it does frustrate me that that shows up for no reason, contextless.
You have to know what Boltzmann's constant is, though, to get the answer.
Oh, yeah, because you have to know you have to look it up, don't you? Yeah. It is in the formula sheet, and you will be given it in the formula sheet, but you're correct, right? Because if I were you, and I were doing this question devoid of context, and I'll be like, is KB some sort of constant that Tom taught us that I don't remember? You're exactly correct, right? So yes, there is exactly one question where KBT, T being temperature, KB being Boltzmann's constant, which is thermodynamics, shows up. And I should say, in the exam, there is a chance that you may see a question like that. Temperature in Kelvin, yeah, exactly. In my head, I put temperature in Celsius. It's temperature in Kelvin. So you have all my apologies. I didn't write that. Yes?
Is that the work equation in the...
Is it in the formula sheet? I don't know. It's worth checking. It's worth checking. It's worth checking what if this is in the formula sheet. I should look that up. I don't know. It's pretty foolish of me, isn't it? I should know these things. Alrighty. Sorry, I'm just checking. We've got our event coming up. Alrighty. So, this is the last question, but because we have no other time, what I want to do is spend this last few minutes going over any questions we have about the entire course, because we have like 5 minutes. Because we could do a calculation. I'd recommend give a try to the calculation in the notes. It's very simple. It's just a numerical substitution. Okay? It's a practice that we understand the substitutions. But yes, double check what's in. God, we have 3 minutes. Okay. What? Yeah, I should make a video of all the examples. That's a good idea. How about post that on the forum so I remember? No, on the forums. Don't post it on Discord because I'll just forget Discord. Post it on the Moodle forums because then my boss will look at it and go, Tom, you've not answered these questions. Okay? My boss doesn't monitor Discord, but my boss does look at the forums and go, Tom, your job is to answer these forums. So do that. No. Anyway, other question. Hi, Tom. You said in the lecture that you'd post a video doing these demonstrations, but you haven't yet. Where is it? But write it nicer than that. Write it like, Tom, can we have a video of you doing the derivations that you didn't make it through in class? That would be nice.
You could post on the forum saying thanks for the video, and then the Discord saying can we please have the video so it makes you look good.
Oh, no, it's okay. It's okay. Because then if you post thanks for the video on the forums, I'll assume I already did it. I have the memory of a goldfish. I don't remember things. That's why I need you to email me anytime I need to do something, because I leave the email unread until I've done it. And then it's a little number. Okay, the other important thing is, don't forget we have free food soon. In G59 at 4:30, we are having Women in Physics trivia, right, for International Women's Day. It's for everyone. No. The questions are about women in physics. Yeah. No. It's open to everyone. That's the second time someone's interpreted the phrase that way, actually. But it's open to everyone, but it's about women physicists. And the prize is a book. Yeah, that's that. So please come to that. It's in G59, which is just on the ground floor here. I'm going to go set up for it now. I will be ordering pizza for everyone based on some university budget I've been allocated. And yes, thank you all for coming. Thank you, and I'll see you later. Never again, actually. Maybe, who knows. Bye-bye. Yay. Sorry? Will you see me at the review session though? Last time I didn't share my camera. I just put it on the recording. Yeah, because I couldn't get the camera to show up on both the recording and the other thing. Tarek, question. Is it? Yeah, so the review session I will record on YouTube and post it immediately to Discord, as I mentioned before. I will post it that night. So, yeah.